Richard Rutledge. This work's done in collaboration with Alex Orso. The work is motivated by a larger project that you're going to hear about tomorrow from Keita. I'll get it. Give me enough iterations. We're all about iterations here. So you'll hear more about the specific motivation behind this work tomorrow. But in particular, of course, I mean, all of us understand the importance of floating point and the difficulties floating point has with symbolic execution. So the issue is, of course, that the floating point semantics are very complicated. They're difficult for a lot of S&T solvers. There are a few now that can deal with it, but Z3 and at least one other. But as an approximate, before floating point was common, as ubiquitous as it is now, there used to be such a thing as called fixed point mathematics. Early processors used this to approximate or to give them approximate floating point mathematics. So this work actually owes quite a bit to Doom and first generation game consoles, laughingly enough. As a background, this is fixed point arithmetic. You can think of it as scaled integer arithmetic. And typically, a common notation is a Q notation where you have a Q m dot n, which means you have m digits or m bits of integer and n bits of fraction. So, and you'll see me, I'll reference that a couple of times. So here's an example program that has a branch statement that depends upon, hey, I got it. Depends on a floating point comparison right here. And going back to, you'll have to get the motivation for tomorrow from Keita, but for now, just assume the fact that KLEE only generates one case makes Keita sad, because it means that he doesn't get exploration of either the true or the false branch. Typically, when KLEE concretizes the double here on access bar, it turns out that Z3 is particularly fond of 0. So these will almost always be 0. So what we're going to do instead is we're going to use a fixed point approximation. So we're going to do a transformation. Now in this case, the transformation, I'm showing you the transformation in C. Understand, please, this is really happening in LVMIR. So we're going to translate the types. The doubles are going to become this constructed type, the fixed 32 type. We're going to translate all of the constants that appear. We also have to translate the operators, all of them. We're going to replace these inline operators with function calls into our fixed point library. Now, and the prototype tool has to go much deeper, has to go even further than this, because you have to translate structure fields, arrays. It's a little tedious, but nonetheless, it's straightforward. Now, you have to do more than just simulate operators. You also have these other non-numbers, these special non-numbers that are defined by IEEE. So these are going to be nans and ints, for example. Now, in reality, it depends on one trade-off you make as you build up your semantic model, which you're going to implement to proxy for the floating point, is how accurate you want this model to be. I mean, actual IEEE floating point has 2 nans, a quiet nan and a singling nan. It also has a couple of ints, a positive infinity and a negative infinity. It even has a couple of zeros, which we saw that coming. But however, each one of these that you implement is going to add complexity, which will either work out as additional states that have to be explored because of the flow control, or additional terms in your path condition, and it would just make life more difficult for your solver. So that's an important question: is how far you want to go in constructing the semantic model. Now, as we already mentioned, because arithmetic for floating point for fixed point numbers is identical to arithmetic for integer numbers, and in particular, I mean addition, subtraction. A floating point addition could be as simple as a plus b. That's arithmetically correct. However, that's still not enough because it doesn't handle, for example, that does not incorporate a model of nans. So you need the nans to behave. So you have to detect if either operator is a nan and return a nan. So now we've introduced flow control, which means we're going to start generating either more states or a more complex constraint. Unfortunately, we're still not there because this still doesn't incorporate full floating point semantics. Floating point can overflow, but overflow does not result in a wrap. Overflow just overflows and you get an error. Integers, so there's no way you can take two positive numbers and end up with a negative number as a result. So that results in noise in your output in places where your approximation is no longer accurate. So you got to detect those overflows. So this is what addition actually turns out to be. Much more complicated process than what we had hoped, but nonetheless, this is still very tractable. Because here you only see a couple of, actually just one branch, two branches. So this is still quite reasonable. Multiplication. Similarly to addition, multiplication is quite simple. Here we have only two branches, so we've added one more branch, one more condition to detect the overflow and to detect nans. Oh, now we get to division. Division's a problem. Division has, here we go. Oh, we got some flow control up here. Oh, we got a while loop there and another while loop up there. So loops are bad. In fact, this generates just simple division. Oh, there we go. Now you can see them. These numbers are slightly stale because I ran this again last night with some other improvements. This generated 160 in my ran last night. Inputs through this a single division. So that's 160 states. So this is a recipe for either path explosion, or if you do the merge, and this is a question that I had for Martin this morning, how well can I expect KLEE to be able to merge 160 states into one? And just square root was just insane. Square root does not finish after 60 seconds. In fact, I ran it for 10 minutes last night, and it stopped with 60,000 states, 30,000 of which at least finished. And I did not have the heart to ask Martin how KLEE merge would like 60,000. So these are a problem. So how do we deal with this? Well, one of my favorite techniques as a practitioner to solve hard problems was to make it someone else's problem. So what does div look like? Well, it turns out division's hard, but multiplication is quite easy. So I just declare a value, tell KLEE that very simple, that if I multiply the result, that value by b, I must get a, and return that. Turns out KLEE's the solver is very good at finding an answer. Straight, and this case, it's still not clear. I mean, it's an open question, I think, as to whether or not this is better than just the brute force division. It's not clear to me, and that's going to have to be some more future work. Square root's not even close. Square root, you go from something that never completes. This with square root completes in moments, as long as you outsource it to KLEE. Outsource it to the solver, excuse me. Yep, okay, so it's good. Preliminary trial. I took the 14 Imperial's 14 synthetic benchmarks used for KLEE float. I had to discard two of them. One of them is very dependent upon the IEEE format for storage of numbers. That one, we would not have explored all states because it was picking apart story representation formats. And I also had to throw out one other, paranoia, and I need a question about paranoia later because I couldn't find any symbolic input. So I don't understand what was happening there. But here are my preliminary results. So here on the in the center column, you see what vanilla KLEE, and with its reported instruction and branch coverage. And in the right-hand column, you'll see for the fixed point flag. The coverage is always at least equal to what was covered with vanilla. I hope you'll forgive vanilla. And sometimes it's strikingly better, such as here, the very first one, count KLEE, 22.2 to 85. Others are 50 to 60, so they're not huge. Sometimes there's no change, such as some is commutative. That's, by the way, that's because there's no flow control, almost no flow control in the benchmark. The benchmark is attempting to measure the completeness of the model more than it is flow. Question?
So just a quick question, keep evidence on these experiments?
Yes, but KLEE, well, let me be clear. I mean, in these cases, what I ran both KLEE and KLEE with my option added for 60 minutes. I just used the standard 60-minute that everyone seems to use, but there is a timeout for all of these. And just for those of you, KLEE, this is implemented off of, my implementation is a fork of latest master of KLEE. And I formulated this as an option flag you add to the command line, does a pre-processing pass to transform the floating point to fixed 32, and then does the execution. And loads the floating point library, fixed point library. But there was a question there.
These coverage results, are they for your, well, both vanilla KLEE and your version reporting their internal coverage?
The coverage reports here are what I would consider to be workshop quality, but not publication quality, because exactly that. These are the internal KLEE's reported numbers, which means because I've added instructions and added branches is part of the transformation. These numbers are indicative, but shouldn't be taken literal.
I hadn't thought of that. That's interesting too. I guess I was thinking, presumably the ultimate goal is if you had a test input that would find a bug or achieve some coverage, would you then try to round that to the nearest floating point and run the original application with the floating point to confirm?
At this point of this process, what I'm attempting to do is just to get the coverage numbers generated. Now, what you do once you have the inputs generated, then that becomes a question. I mean, you could do a replay to see if you could reproduce the issue. If you found some property violation or some behavior that you want to verify, you would take the fixed point number generated by this process and translate it back to a floating point representation. Now, another alternative is to record where those translations have occurred, and then simply convert it on generation of the test case, of the test input. And then you can play it back. In particular, my other work is on differential testing. So I'm driven to do that differential testing. I'm driven by inputs. I need inputs so I can play back. And of course, as you'll learn about this project tomorrow, this project is floating. This is a floating point rich environment. And as it stands right now, I'm probably going to get almost no inputs. So next step within will be applications of the numbers generated. Now, in summary, there are many advantages to doing this, to the fixed point approximation. It does give me higher coverage. It does not require a heavyweight solver. For example, the solver I used was just STP. STP is perfectly, in fact, I found STP to be lighter weight and faster. I get better results with STP than I do with Z3. Because I'm not, even when I use Z3, I'm not using any of the Z3's extra capabilities. So this does not require a heavyweight solver. However, there are some risks because I'm approximating. That means that when you play it back, you may not, it's possible there's going to be a divergence. It's also, again, approximation. There may be issues with underflows, overflows, and that it looks like an underflow or overflow to me with this approximation, but would not actually underflow or overflow real floating point. Some floating point errors, I may not be able to detect because I don't have the high enough granularity. One of the benchmarks, as I recall, adds a very small number and it determines what the loop. It so happens the very small number isn't too small to convert to a real fixed point number, but would have been very unfortunate if it had been 10 to the minus 50, in which case I would have converted it to 0. And suddenly had an infinite loop. So one of the other pieces that I'm interested in knowing is what kind of errors can I detect with this approach. So we'll find. Hopefully I'll find out about that in the coming year, and turn him from sad to happy.